So let's talk about graphing f of x equals 3e to the negative x squared. We're going to go through all those steps. We're going to find all 7 pieces of information again, and then go for the graph. This is an interesting run with e. Pretty intimidating if somebody walked up to you and said, "Hey, could you graph this for me?" Just by hand, no technology. Well, after this, you'll be able to do it. Okay, let's take a look. The first aspect is the domain. Well, here, all x values are fine. The domain is all real numbers, or you might say negative infinity to infinity. Next up, the intercepts, beginning with the x-intercept. So if you recall, we set y equal to 0 and solve for x. Now let's take a look how this plays out. 0 equals 3e to the negative x squared. So, of course, you could divide by that 3. Right. Then to cancel the e, you might take a natural log. But when you take the natural log of 0, that doesn't work. And if you don't believe me, take a look, put that into a calculator. The natural log of 0 does not exist, or you might say it's undefined. So that leads us to say there is no x-intercept. It will never pass through the x-axis. Turns out this will never equal 0 because any value you plug in for x is always going to get you a positive, even though there's a negative sign there. The whole thing, when you're done with the e, will be a positive number. Anyway, let's move on to the y-intercept. And we're going to do the opposite. We're going to plug 0 in for x. This one tends to be the easier route. And solve for y. 0's in there for x. Hey, negative 0 squared, that's e to the 0. And you might know that anything raised to the 0 is 1. So we've got 3 times 1. Our y-intercept here is the point 0, 3. Okay, so it might turn out that you don't have any x-intercepts, right? I mean, that's definitely a possibility. There will always be a y-intercept, I guess, unless it's the case where there's a vertical asymptote there or something. I guess, granted that the y-axis is in the domain, it is going to have to cross it, but not necessarily the x. Okay, moving on. We'll talk about asymptotes. Any vertical asymptotes? Well, considering that function, no. Vertical asymptotes occur when you divide by a factor. And here we're not dividing by anything, so there aren't any. Horizontal asymptotes, though, will always give us some information. Even if there aren't any asymptotes, like we saw in the last problem, we can at least find something. Okay, so here, horizontal asymptotes, we're going to begin. I'm going to cover this up with my old, very used eraser. So, okay, we're going to take the limit as x goes to infinity for a function. Now, we did a couple things like this very briefly back in 3.1 when we first started talking about e. Think of 3e to the negative x squared, so that negative exponent, think of it as 3 over e to the positive x squared. And now I'm telling you the answer is 0. Well, we talked about this sort of thing then. What's happening is the infinity goes in to the exponent. Well, infinity squared is infinity, so I've got e raised to the infinity. But that's going to infinity. But I'm dividing by that. So I've got 3 divided by infinity. So my denominator is getting really, really big. If I take a number and I divide it by a really big number, that whole thing gets smaller and smaller. It heads towards 0. So my answer there is 0. Okay, let's do the same thing but with negative infinity. We need to think about what's happening the other direction. As x approaches negative infinity, well, I'm going to do the same trick, 3 over e to the positive x squared. But now if I take negative infinity and put it in, I'm going to get the same result because, well, negative infinity squared is positive infinity, and e to the positive infinity is infinity, and I've got this same logic there. So here we do have a horizontal asymptote. You might say the horizontal asymptote is at y equals 0. Or what might make more sense graphing-wise, you might say, hey, as x approaches infinity, the y value approaches 0. And as x approaches negative infinity, the y value approaches 0. In both directions, the y value is going to level off at 0, or the x-axis. Okay, so obviously we're about to gather a lot more information, so we're just going to be sure when we go to graph that this really is working out, or at least we need to make sure our graph fits this information here. Okay, that's all for the original function. Let's move on to what we can learn from the first derivative. Let me write the original function here again. F of x equals, what was it again? 3e to the negative x squared. Okay. Again, I'm assuming everybody is a derivative master, even though I know that's not really the case, but it needs to be. What rule would you apply to this? It's the chain rule that is inside. The e is the outside. Okay. And the 3 is just a constant multiples. Okay, so the 3 is just going to go along for the ride, if you will. The derivative of the outside, we always, if it's e, right, we copy it, multiplied by the derivative of our inside, negative 2x. 3e to the negative x squared times negative 2x. Now let's clean that up a bit. The first derivative is negative 6x e to the negative x squared. Okay. Now what can we learn from this? We'll go to the intervals of increasing and decreasing. So I'll just show you all this here. We're going to set our derivative to 0 and solve. Now, when you set that derivative to 0, think of it as two factors. All right, it's like it's already factored. So I can take that equal to 0, and I can take that equal to 0. Well, the first one's pretty quick to solve. Negative 6x equals 0 gives me an answer there. E to the negative x squared equal to 0. Well, we come to the same issue that we had back for the x-intercept. There's no way this can happen. If we were to take a natural log of 0, it'd be undefined. So that does not give us any solutions, although we do have one here. Okay. Then we're also going to consider when the first derivative does not exist. Well, it's just off the screen. When that first derivative, well, yeah, we're never dividing by an x or anything, so there's not any answers that come out of this. But we do have that one critical number at 0. Okay, so we're going to go ahead and draw our line. Let me get this off the screen. We don't need that anymore. Okay, so we're going to draw our domain. Our domain was everything. And we're going to mark 0. And then we're going to plug in numbers on either side. I'm just going to show you all I got here. Okay, so I picked -1 and +1. Okay, I plugged them into that derivative. So when I plugged in -1, negative 6 times -1 e to the -1 squared, well, that's going to be +6. This is going to be -1, 6e to the -1st. Turns out that's 2.21. I went ahead and got the decimal approximation just to be absolutely sure that that was a positive number. In case I didn't recognize it as positive here, if I put it into a calculator, that'll be good enough. It's a positive. That's all I need to know. And for, on the other side, x equals +1, putting that in, very similar, -6 e to the -1. Well, this is a negative because of that negative out front. It would be -2.21. So there's a negative there. And that tells me my intervals of increasing and decreasing. Increasing, decreasing, increasing negative infinity to 0, decreasing 0 to infinity. Fairly simple. We also want to chat about local maxes and mins. So at 0, it's switched. we're going to say, okay. Then at 0, it was increasing, then it started decreasing, so there was a local max at 0. But I need the y value, so I'm going to put it into the original function. When I do that, I get 3 e to the 0, which is 3. There's a local max at 0, 3. And we saw that point earlier. That was our y-intercept. Just kind of connecting the dots. Not unusual for these points to repeat, that a local max is the same as our intercept. Doesn't always happen, but doesn't shock us either. Okay, now we need to go on to the second derivative. Oh, there's our first derivative. I repeated that, so here comes our second derivative. Of course, I'm assuming you're a derivative master. How did we get to the second derivative? Well, what rule would apply to our first derivative? And it's a product rule. It's my first function multiplied by my second function. Put a dot there. So I've got the derivative of this one times that one left alone, plus, and I copy this, and the derivative here, hey, I've taken that derivative before. That's a chain rule, the outside times the inside. I should say derivative outside times derivative inside. Okay, now let's clean that up a little bit. Of course, I don't need the dot there. This becomes positive 12x squared e to the negative x squared. That's about as good as we're going to get. Okay, so where are we going next? Intervals of concavity, and I'm just going to show you everything. Oh, kind of getting some shadows here with the afternoon sun. Apologize for that. Let me try and get my cord out of the way a little bit. Oh boy. Okay, well, let me just kind of pull this up. I think you can see that well enough. There's a little bit more on the page. I'll pull it up in a second. So let's talk about when the second derivative equals 0. So I've got my second derivative equaling 0. Now what I can do, it's all about factoring, right? So I'm going to go ahead and factor. I can take out a negative 6, and I can take out that e to the negative x squared. That leaves me with 1 minus 2x squared. Okay, once I have that factored, I'm in a pretty good spot. I'll set the first factor equal to 0. But again, we see that e to the negative x squared equals 0 can't happen. This will not produce any solutions. But the second one will. 1 minus 2x squared equals 0. So let's see, I can add that 2x squared, divide by 2. And now it's starting to get a bit blurry and in the shadows. So dividing and then taking a square root. Okay, so I've got, don't forget your plus or minus. I've got plus or minus the square root of 1/2. Now the thing is, we're going to have to graph this in a moment, and I don't really know what that number is, so I'm going to go ahead and put that in a calculator. And it's going to tell me x equals plus or minus 0.71. So that's going to be a little bit more useful. You could even go with plus or minus 0.7. Even 1 decimal place would be fine for graphing purposes. I went ahead and did it to 2 when I rounded. Okay. Of course, we don't want to forget about when the second derivative might not exist. But our second derivative, we're never dividing by anything, so that's a none. Okay, so we got these 2 values here we're going to put on our domain line. That's coming up next. Right, I got my domain line. Negative 0.71, positive 0.71. And why don't I just go ahead and show you all of my work here. If it'll fit. Oh, it won't fit. There's too many. There's 1, 2, 3. Will it fit? That third one barely, but it's in the shadow. It's in the shadow. That's okay. So I picked, because I know the decimal values, I can pick these easily. Negative 1 into the second derivative. Let's see, negative 1 in there, negative 1 there, and all the x's. Negative 6 e to the negative 1 plus 12 e to the negative 1 gives me positive 6 e to the negative 1 when I add them. and that's a positive result. Okay, putting in 0 for the middle section. Negative 6 e to the 0, 12 times 0 squared e to the 0. Well, that's gone, and it's just negative 6. Okay. Negative. And finally, positive 1. That gives me the same result as negative 1. This is a positive also. Okay, positive, negative, positive. Well, there's my concave up, concave down. That's what I wrote here. Concave up from negative infinity to negative 0.71, union 0.71 to infinity. It's on the outsides. And in the middle, concave down. Okay. Last but not least, it's the inflection points. Hey, it changes. It changes at these values, right? That's where it switches, and there's nothing else going on. It's not an asymptote or anything like that. It is in the domain. So those are both inflection points. At x equals negative 0.71, I'll plug that into the original function, and I got 1.81 when I rounded that to 2 decimal places as well. X equals positive 0.71, I put that into the original function as well to get the y value, and I got the same answer because there was a squaring in there. So these are both my inflection points. Okay, now we got to graph it. So I went ahead and got it started. So if you just go through all the information we found, first thing we found was that 0, 3's are y-intercept. There were no x-intercepts. Turns out, makes sense there's no x-intercepts because that line y equals 0 was a horizontal asymptote. So it turns out everything's going to be up above here. It's never going to pass through. Okay, then I just plotted our inflection points as well. That was our local max also, so there wasn't anything new. Then we had our inflection points. Okay, then we'll go and think about increasing, decreasing, and concavity. So we found that it's increasing until we get to 0. So we're going to increase all the way up to the 3, and then we're going to decrease. Of course, we'll pass through our inflection points. And then it was concave up here, concave down, concave up. So here's what it's going to look like. It's got that asymptote, right, going back this way, and then it's going to curve upwards and increase. Then at that moment, it becomes concave down as it hits that peak. Okay. Concave down all the way to here, the next inflection point, and then it's going to go back to concave up, although it is headed down, decreasing towards that asymptote. So I've got increasing, decreasing, concave up, concave down, concave up. I've got my asymptote and all of my points. There's the graph right there. Not a bad job for not having any kind of graphing device. We did this all by hand. Can you believe it? When you're doing homework, I strongly recommend go to Desmos and graph there. Do all the work. I recommend do all the work first by hand. See what you get. And then when you're done, go and confirm. Or if you run into an issue and you just can't seem to go around it, go ahead and go graph. But best case scenario, you do it all correctly, and then you go and confirm that, and you get that reward. That's the end of this section. I'll see you guys in the session. Good luck in homework.